Hey everyone, and welcome. So, you're building sequence to sequence models, but you're looking to really push them to the next level, to go from kind of working to, wow, that's actually really good. Well, you are in exactly the right place. Today, we're going to level up your training game with some seriously powerful techniques. Okay, let's start with a problem that I'm sure feels super familiar. You've built your model, maybe a chatbot or a translator. You feed it all this data, you hit the train button, and you wait only for the output to be, well, complete gibberish. It's so frustrating, right? But believe me, you're not alone, and the good news is there are some really elegant ways to fix this. So let's just dive right into those solutions. We're going to walk through three of the most effective techniques out there by tackling the exact questions you're probably asking yourself right about now. All right, first up, let's talk about that painfully slow training and how early mistakes can just completely derail the whole process. The fix for this is a really clever technique, and it's called teacher forcing. I mean, this is the fundamental issue, isn't it? When a model is just starting out, of course it's going to make mistakes. But in a sequence model, one tiny error right at the beginning can just snowball into a total catastrophe by the end. So, how do we stop that from happening and just get the model on the right track way faster? The answer is teacher forcing. Here's the idea. Instead of letting the model feed its own, often wrong predictions back into itself while it's training, we step in. We act like a teacher. At every single step, we give it the actual right answer, the ground truth, as the input for its very next step. This just helps it learn the correct patterns so much faster and with way more stability. You know, a really great way to think about this is like putting training wheels on a bike. You're giving the model this constant guidance, preventing those big, catastrophic falls that come from early mistakes. This lets the model focus on what it's really supposed to be doing, learning how to generate the sequence. And the result? It learns way, way faster. And this comparison here really just lays it all out. Look on the left. With standard training, one little error feeds back in, and boom, you get a cascade of mistakes. But look on the right. With teacher forcing, we completely break that vicious cycle. By feeding it the correct answer every time, we make sure every step is built on a solid foundation. Okay, so we've sped things up. That's great. But now a new problem pops up. Sometimes the model starts out strong. It's generating really good stuff, but then it just seems to lose the plot. It completely forgets the main point of what it was asked to do. Yeah, this happens all the time, especially with longer sequences. The decoder gets that initial context vector from the encoder, its starting orders. But as it generates more and more words, that initial message just gets weaker and weaker. It gets diluted. So how do we keep the model focused on the original mission? We can solve this with a technique called peaking, and it's pretty much exactly what it sounds like. We let the decoder peak at that original context vector, that little summary of the input, at every single step of the generation process, not just at the beginning, but all the way to the very end. This whole process basically gives the decoder a cheat sheet. That context vector is the summary of the original request. So instead of just getting it once and having to remember it, we let the decoder keep it on its desk the entire time it's working. It's a constant reminder that ensures it never loses sight of the main idea. Okay, so we've boosted speed and we've improved context. But this leads us to the biggest challenge of them all, handling really long sequences. I'm talking about translating a whole paragraph, for instance. This is where standard models just completely hit a wall. And here's why. It's a fundamental limitation. Trying to cram the entire meaning of a long, complex paragraph into one single fixed-size vector, it's a huge bottleneck. It's like trying to summarize an entire novel in just one sentence. You're going to lose so many crucial details. Even powerful LSTMs start to forget things after about 30 words or so. It's just too much to hold in one place. So that brings us to the big question: how do we get around this bottleneck? How can a model possibly understand that the 50th word it needs to generate is directly related to the second word of the input? We need a much more dynamic way for it to access that original information. And the breakthrough solution to this is the attention mechanism. It's a total game changer. Instead of forcing everything into one static summary, attention gives the decoder the power to look back at the entire input sequence, at every single step. And as it does that, it figures out which of those input words are the most relevant for generating the very next word in the output. Honestly, the absolute best analogy for attention is a spotlight. Imagine as the decoder is writing each new word of a translation, it can shine this spotlight back on the original sentence.
it can focus that beam intensely on just the 1 or 2 words that are most critical for that specific moment. This is what lets these models handle incredibly long and complex sentences and paragraphs. All right, let's bring all this together. These 3 techniques, teacher forcing, peaking, and attention, they really form a powerful toolkit that you can use to build truly state-of-the-art sequence models. And this table just sums it all up perfectly. If you're dealing with slow training and cascading errors, use teacher forcing. If your model keeps forgetting the big picture, try peaking. And when you're taking on those really long and complex sequences, the attention mechanism is absolutely your best friend. Each one tackles a very specific bottleneck in the process. So, why does all this matter? Well, because these aren't just some abstract ideas. These techniques are literally the engines behind the most advanced AI applications that we use today. They're what make machine translation so much more accurate, what make chatbots feel more coherent and less forgetful, and what allow Q&A systems to actually understand complex documents. And hey, if you found this breakdown useful, it would be awesome if you could hit that like button, share it with anyone else you think might find it helpful, and of course, subscribe for more explainers where we break down these complex topics into clear, easy to understand pieces. So I'll just leave you with this one question to chew on. Attention gave our models a kind of dynamic memory. Now that they can focus, what do you think is the next great barrier we need to break down to create conversations that are truly, genuinely indistinguishable from a human's? Thanks for watching.